Today, I'm going to shine some light on an amazing concept that has horrifyingly incredible consequences for all of science! 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 I really do have to get an echo machine, a reverb. Topic 5.02 light. What the heck is it? And what can you use it for? It's actually very useful, not just for seeing. You see, when I say, hey, I'll see you later, what you're saying is that you promise that at a further point along in the timeline, light will reflect off of that other person and into your eyes, sending a signal from your optic nerve into your brain where it will process it and say, hey, I know you. Light. Now, what exactly is it? Well, it's a form of energy. And here's where it gets really weird because light is like, I like to think of light as tracing the outlines of the universe itself. It's made of particles called photons. They're tiny little packets of, well, remember in the last unit when we did E equals MC squared, we just said that mass is just a super concentrated form of energy. Well, light is the most light mass there is. Nothing has less mass than light. In fact, it's typically considered to be massless, and yet it still has a limit on how fast it can go. We call the fastest speed that can be gone, and that's what's the speed of light in a vacuum. These are supposedly photon torpedoes from the original Star Trek. They're not photon torpedoes because they're actually just torpedoes. But anyway, they travel in waves. Whoa. Remember we talked about Louis de Broglie said everything travels in waves? Well, light travels in waves. Look at that. Waves. Waves. And it travels at the speed of light, which is 300 million meters per second. How fast is that? Well, you know what a meter, right? How long a meter is? You see a meter stick? Well, it travels 300 million of those in 1 second. Yeah, that's wicked fast. Even though it's fast, it still takes 8 minutes for the light of the sun to reach the earth. Because it's not infinitely fast, it's just the fastest thing there is. Well, the Millennium Falcon, what are you going to do? Now, this is how light forms. We have electrons that are in the lowest energy levels that they can theoretically occupy. These are called electrons in the ground state. And they're content to stay in the ground state forever. However, if you give them energy from an outside source, and it can be in the form of heat, light, or electricity, the electron will absorb that energy. And just like when you kick a ball, it goes up in the air, the electron will move further from the nucleus, increasing its potential energy. Remember, opposites attract. So now this electron has more potential energy than it had before. And it's now in what's called the excited state. Now, it does not stay there for long. In fact, almost immediately after rising up in energy level, the electron expels that energy. It's like taking a breath and expelling a breath. The energy that was gained by the electron gets lost. The electron falls to the ground state, and any energy that that electron had picked up is released in the form of light. Now, it doesn't matter what form the electron originally absorbed that energy in. When the electron falls back down, it's always released as a photon of light. And the energy of the light, which can be distinguished by its color, is dependent on how far the electron fell. If it only fell a little, then low energy light will be given off. If it fell further, then higher energy light will be given off. Now, does that mean the light is brighter? No. Energy has nothing to do with the brightness of the light and everything to do with the color of the light. And the human eye is only capable of picking up a teeny tiny fraction of that light. For example, your ear can only hear a certain range of frequencies. Your dog or cat can hear much higher frequencies than your ear can. Now, imagine, if you will, that you have an 88 key piano keyboard stretched out in front of you. Your dog can hear keys on that keyboard if you added an extra several dozen keys above the highest key, higher than you would even be able to hear. Your dog would be able to hear it if you played a song on those higher keys, even though you can't hear it yourself. Now, if we translate that into light, if all light was an 88 key piano, the human eye wouldn't even be able to detect one key's worth of energy. We are not very good at picking up different types of light. The light we can see is called visible light. Well, I guess they couldn't come up with a better name for it. But there's all kinds of light that we can't see, but we have developed the technology to detect it. These are the different kinds of light you can have. Now, they're all made of photons. They're all traveling the speed of light, but each has its own unique amount of energy. What we see in the visible light, red has the least energy, orange, yellow, green, blue, and violet has the most energy of any light that we can see. Now, let's say we venture past the range of human vision. With less energy than red is infrared. Anything that gives off heat will emit infrared radiation. We also use this for remote control devices if we want to turn our TVs on and off. You might look at the front of your remote and see like a little LED in front there. Well, that's an infrared LED that sends a signal pulse to whatever device you're controlling. With less energy than infrared is radar. Radar is used to bounce off of objects to figure out how far away they are or how fast they might be moving. Microwave radiation has less energy than radar and is used for communications or for cooking food because it turns out that microwave radiation stimulates water molecules to vibrate faster, thereby making them hotter. And with less energy than microwave is radio. And radio spans a huge range of frequencies and uses, anything from radio to television broadcast to Bluetooth to Wi Fi to 4G and 5G and pretty much anything you can imagine. With less energy than visible light, we have ultraviolet. Ultraviolet is very damaging because it gets absorbed by our skin and it can cause sunburns, skin cancer. It can even get into your eyes and cause cataracts. Fortunately, we don't receive all the ultraviolet that our sun provides. The ozone in our upper atmosphere blocks a lot of it. With more energy than ultraviolet is X rays. Yes, the ultraviolet can be absorbed into your skin, but X rays will pass through your entire body, with the exception of your bones. Your bones are dense enough to stop X rays. However, you would be completely invisible to gamma rays. They have so much energy, they just pass through you like you weren't even there. So, from the lowest energy to the highest energy, there you go. Gamma rays, X rays. This person definitely did not have a good day. Ultraviolet, visible light, infrared, radar. This is Doppler radar indicating a tornado near Greensburg, Kansas. That was a devastating tornado. Microwave and radio. These are all the different wavelengths, energies, frequencies that light can have. And we can only directly detect the tiniest part of it. One note in a trillion. We can use these forms of light to identify elements. You see, every element has a different number of electrons, and every element's energy levels have a different amount of energy because of nuclear charge. We'll explain that a little bit later. So, the first, second, and third energy levels of hydrogen will have a different amount of energy than the first, second, and third energy levels of helium. Because of the higher nuclear charge of helium, helium's energy levels are pulled a little closer to the nucleus and to each other. Hydrogen's energy levels are a little bit more spread out. So when an electron falls from the third to the second energy level in hydrogen, it's going to give off more energy than an electron falling from the third to second energy level of helium, which means that every element will give off a different characteristic color light when you heat it. And if you pass this light through a prism or a diffraction grating, you will get individual colors, a partial rainbow. Instead of the 88 keys on the piano, you may only be playing 8 of those 88 keys, or 2, or 7. So here's how it works. We have a high voltage source, and we're going to add electricity to the element in a discharge tube. The light will pass through a slit and into a prism, which splits the light into its component parts. This high voltage discharge tube contains hydrogen. Hydrogen emits red, green, blue, and violet in the visible range. These are the different colors of light we see from hydrogen. It also emits colors in ranges in ultraviolet and infrared that we can't see directly, but we have been able to detect it. So how exactly is it that we form these 4 colored lines at 411, 434, 486, and 656 nanometers? Well, here's how it works. When an electron drops from the third to second energy level, red light is given off. When an electron drops from the fourth to the second, green light is given off. When it drops from the fifth to the second, then blue light is given off. And when an electron drops from the sixth to the second, that's when violet light is given off. Now, what about if it drops from the second to the first? Well, that's a much bigger drop in energy that would produce ultraviolet light. So any of these longer drops to the first energy level would produce lines in the ultraviolet spectrum. What about shorter drops, like drops between the sixth and the fifth energy level? Well, that energy level drop is so tiny that it would show up in the infrared range. We wouldn't be able to see it directly. So these are the only energy level drops that we can directly pick up with our eyes without the aid of any kind of technology. And we don't need to go further than this because no other element produces this specific spectrum. You can actually say that the bright line spectrum of an element is the element's fingerprints because it's unique to each element and can be used to identify an element. And that is all there is to light as far as this course is concerned. You may go deeper into light and actually calculate frequency and wavelength of different specific kinds of light, but we are not going to go into that depth in this class. To do that, I'd recommend you take physics next year. Physics is the science of how toys work and everything else. Next up, we're going to take a look at how atoms are put together, how electrons fill up in atoms in energy levels. But until then, take care. Say hi to everybody for me. They have no idea who I am. And most importantly, bye.